Hi everyone, I'm Dr. Surjit Singh. In this video on Python via examples, I'm taking one of the most important computer programming topic, that is the recursion. Let us begin. In this session, we will discuss about recursive formulas, edge cases and call stack. We shall compare recursive and iterative methods and about advantages and disadvantages of using recursive methods. We shall take examples of factorial, x to power n, and of palindromic strings. Recursion has been known in mathematics since a long time, and it is available in all the modern programming languages. Recursion means a function calling itself. Most common example for introduction to recursion is of the factorial function. Factorial is not defined for negative integers. Let us not import it from a library and write our own function for finding factorial of a number. Before coming to recursion, let us discuss its iterative solution. Main program passes 4 as a parameter to the function fact. First of all, we must validate the argument n. For valid values of n, we start with result equal to 1 and start iterations in a loop. I values will iterate from 2 to n, so we do not enter the loop if n is less than 2. Each time we multiply the result by I. For n equal to 4, I takes values 2, 3, 4, so result becomes 24 and we return the result to the main program. In Python, there is no limit on the size of an integer, but the time of processing is very high if n is in thousands. For other languages, there is a limit to the size of integers. Let us now learn about recursive solution. We can divide the expression of factorial 4 into two factors. This shows that we can express factorial 4 to be 4 times the factorial of 3. In general, factorial of n is n times factorial of n minus 1, and it covers all cases for which n is greater than 1. Exceptions are the two edge cases in which n is either 0 or 1, for which we do not need recursion. We classify these relations into three cases. Error case remains the one for which n is less than 0. Edge cases are for which we know the solution and we do not require recursion. For all the remaining cases, we apply the recursion formula. Let us incorporate these cases in our factorial function one by one. Note that the main program remains the same. It will not know whether we are using the iterative or the recursive approach in the factorial function. Even the error case remains the same. The two edge cases can be combined in a single statement. Recursive case is invariably the last part of all the recursive functions. Ultimately, all recursive cases must reduce to an edge case, otherwise the process will become endless. In this program, the three cases are clearly differentiated in the three segments of the if statement. We must test each case of every program thoroughly. In this program, values of n equal to -1, 0, 1 and 2 are the minimum essential for testing it. The for loop is gone. Therefore, the recursive program looks simpler. However, computations are the same in both the methods and the time of execution also remains the same. Recursive programming needs more care. If the execution does not ultimately reach an edge case, it becomes endless. In the present program, we do not have to worry in this respect because n is decreasing in every recursion and will eventually reduce to an edge case. Let us now carry out the dry run of our program. Main program calls fact for n equal to 4, which becomes parameter of function fact. It is not negative and is not less than 2. We skip the first two if cases and reach the statement to return 4 into fact of 3. We must know fact 3 before we can evaluate the return expression. So we make another call to factorial. This time we allot a new chunk of memory to pass 3 to the parameter n. Once again, this parameter is not wrong and is not less than 2, so we return 3 into factorial 2. Factorial 2 makes yet another call to the same function with n equal to 2 this time. This makes yet another call to fact with n equal to 1. This time the argument is less than 2, which is an edge case. It is non-recursive and we directly return 1, which we pass back to the function that called it. This replaces fact 1 in the expression with 1. The present call of the function ends. We release the memory associated with this call. Memory allocation follows the rule of last in first out like stacks. So we name these memories as the call stack of the function. A result of 2 into 1 is 2, which becomes the return value of this call of the function. We end this call after passing 2 to the function that called it. We replace fact2 with 2 in the previous call and then remove this call from the call stack. Product of 3 and 2 is 6, which we pass back to fact3 of the previous call that had called it. This call also ends after replacing fact3 with 6, and the result of 4 into 6, that is 24, becomes its return value. Factorial 4 was called by the main program, so we get 24 as the final output. The call stack of the function fact now becomes empty. A question arises here. Why are we checking the case n less than 0 in each call? It is a wastage of time because the checking is not needed in every call. To check it only once, we split the function into 2. Fact now is a non-recursive function that checks the error case and then calls the function factrec. Factrec is the recursive function. It only caters to the edge cases and the recursive case. Let us now compare the recursive and iterative methods of programming. Total computation is same in both the methods, so the time of execution is same. Recursive method needs additional memory for call stack that is proportional to n, and we also waste some additional time in maintaining the stack. But the advantage of recursive method is that program looks simpler and clearer. For certain problems, non-recursive programming is nearly impossible. However, for others, we should prefer the iterative approach unless it is too complicated. Let us now consider another problem that is of x to power n, where n is a positive number. We can split it as shown. The iterative solution to this is simple and the result of this is slightly more than 8. Let us now discuss its recursive solution. This is the recursive relation for n greater than 0, while the edge case is when n is equal to 0. We can now write the recursive program for this. When n is 0, we return 1, otherwise we return the recursive relation. The question left is, what will happen if n is negative? This time it is not a wrong parameter as its value is known. We incorporate it as a special recursive case. This is called only once to make n positive if n is negative. We can test this program for various values of x and n. What happens if both x and n are 0? I leave it as an exercise. Call stack memory is of size n. Time of execution is also proportional to n. With a modification in the recursive relation, we can have a drastic improvement in time and memory from n to log n. And remember that log of 1000 is 10. For this, let us have a look at the new recursive relation. Instead of decreasing n by 1 in every call, we reduce it to 1/2. So the process is over in log and time. Corresponding changes in program are shown here. Not only faster, this approach is accurate also as truncation error depends upon the number of computations. Last problem that we take here is of palindrome string. Palindrome string means that it remains same if we reverse its characters. Let us first write its iterative solution. Length of string is 7. Integer half of 7 is 3. Middle character is always palindrome, so we shall compare these three characters only with their counterparts. To be sure, let us print them before proceeding further. S0 is the starting character, while Sn-1 is the last character. When I is 0, we print them both. When I becomes 1, the characters are both B, while when I becomes 2, the characters are both C, and the loop ends. The central character is always palindrome and we do not have to check it. If at any stage the two characters are not same, the string is not palindrome and we return false without proceeding further. If all pairs match with each other, we come out of the loop and return true as the answer to the palindrome string. We now go ahead with the recursive program. The string is palindrome if its two end characters are same and its mid slice is palindrome, otherwise not. The two edge cases are when the string is either empty or it has only one character. In both of these cases, the string is palindrome. Let us now start writing the program. M is the index of the last element of the string. M is -1 for the first edge case and 0 for the second edge case. In both these cases, string is palindrome and we return true. In the recursive case, if characters at positions 0 and m are same and the slice from 1 to m-1 is palindrome, we return true. If either of the two relations on the two sides of AND is false, then either the two end characters are not same or the mid slice is not palindrome. So the string is not palindrome. Function call from main program is like this. First part of AND expression is true, so in the next call we test BCDCB to be palindrome. The process continues till only one character, namely D, is left. Finally, the return expression will become true and true, which is true, and it becomes the output. In this session, we introduced recursion and its used in programming, edge cases, and call stack. We compared the recursive and iterative methods to know about the advantages and disadvantages of recursion. We took examples of factorial, x to power n, and of palindromic strings to discuss these points. Thank you for your time. I hope you enjoyed the video. Please feel free to ask for further clarifications on my email address given below. Please stay tuned for more such videos.